Okay, well, thank you very much for welcoming me to Devoxx. I've been coming to Devoxx actually for a number of years now, so it's quite a privilege to be on this side of the podium for the first time. Just as a quick question, could I get hands up if anyone's actually heard of CERN before? Okay, great, most of you. That means I brought the right talk then, that's good. Okay, so well, for those of the few of you who don't know what CERN is the world's largest particle physics research laboratory, situated in the heart of Europe, near the city of Geneva, Switzerland. But in fact, this talk starts right at the beginning of time, back when it all first began. When the whole universe was in a hot, dense state, when nearly 14 billion years ago, expansion started. Wait, isn't that the Big Bang Theory? Well, actually it is an excellent show, but not this one. In fact, it took me quite some time to realize that this wasn't actually a documentary. If you've met my family, you'll understand why. But no, what I want to tell you actually is a little bit about CERN from the other side. CERN is an organization. Tell you a few things about CERN probably that you don't already know. As I said, CERN is located near the city of Geneva in Switzerland. This is the main campus of CERN. There's around 12 to 15,000 people who are working here all the time. So unsurprisingly, it's a little bit like a small town. We've got our own restaurants, of course. There's 3 of them on site. In fact, quite a lot of the physics discoveries actually take place not in the particle detectors, but actually sitting discussing around about lunch in the lunchroom. But not only that, we actually also run the biggest hotel in the area, 450 rooms on the local site and another 150 rooms just off-site in nearby France. We have our own medical service. We've got our own fire brigade. We've got our own ambulance service, in fact, as well, run by in conjunction with our local hospital. Of course, as a research organization, we have a huge library as well. But even we have our own on-site store. 16,000 items are available for distribution within our on-site store. In fact, we even have our own kindergarten for the local staff to keep their kids. My kids went to that kindergarten as well. It's truly a unique place. Our internal transport service moves 180,000 parcels, everything ranging from postage all the way up to parts of the accelerator and detector around the site every single year. We're one of a handful of places in Europe with our own 400 kilovolt electrical installation with a capacity of 200 megawatts. And as an organization that literally spans the border between France and Switzerland, we have our own international border, one of unique in the world, which is guarded by a private company. In fact, even if gardener who cuts the grass has to worry about the international transport of waste as he has to dispose of the grass clippings. It's truly an unusual organization, unique in the world. And from the mundane to the highly complex, CERN is a place of extremes. We have civil engineering projects, building structures, underground structures, the size of cathedrals. And at the same time, these huge devices are used to study phenomena at the microscopic and subatomic scale. CERN is a European organization. It was one of Europe's first joint ventures created over 60 years ago now, just after the Second World War. And the vision was to put countries and scientists together, to work together, to try to understand the universe better, and at the same time share that information freely with the rest of the world. Today, there's someone from almost every continent of the world working on CERN's various activities. In fact, it was because of this widespread community of over 12,000 scientists that CERN scientists Tim Berners-Lee and Robert Cailliau invented the World Wide Web. It's hard to imagine the world today without the web. But when I first arrived at CERN back in the early 90s, the World Wide Web was just being developed. Tim Berners-Lee was working on his first web browser on his next workstation. And beside him here is a friend of mine, Nicola Pello, and she was working on another tool that I was helping her with, which was called the line mode browser. This was at a time when most people accessed the computer systems through terminal servers using VT100 terminals, and this was what the web looked like then. This was long before the days, of course, with underlined hyperlinks, and in fact, if you wanted to navigate, using a new verb at the time, you typed in the number at the bottom of the screen in order to browse to the next page. Okay, the world has come a long way since then, and CERN has been at the center of many innovations from special techniques we're using compact particle accelerators for nuclear medicine, to special medical imaging technologies, which was developed using the detector technologies actually developed at CERN. And even mundane things, you might say, such as high-precision welding. There are 40,000 leak-tight joints when we were constructing the LHC, and we had to develop new techniques in order to do the welding, in order to make sure that this all works correctly. This is a photograph actually from 1975, long before I arrived at CERN. And in the guy's hand here is a trackball. Okay, maybe not all that unusual these days, but probably what more interestingly is this one here. This is actually a capacitive touchscreen, a technology invented at CERN and is now a ubiquitous part of practically every single mobile phone. I couldn't resist this photograph actually. This is from the early 1970s as well. This was the control room for the super proton synchrotron. I couldn't resist for the lovely yellow color scheme with the yellow underlights from the 1970s. And in fact, this console, although it was built long before I arrived, it was actually still in place when I arrived in the early 90s. And I remember my first boss who was explaining to me that the software team had actually developed an application that would put a little sailing ship on one of the screens on the left-hand side there, using a programming language long since forgotten called Nodal. And the little boat would then sail across each of the screens one by one, much to the annoyance of the operators who were actually trying to get their job done. But CERN's job, although we're very proud of all of these innovations, CERN isn't there to do applied research. The kind of research that you would do in industry, which you can make great innovations, but you can't make the great leaps of understanding without fundamental physics, without fundamental research. And that's what goes on at CERN. To paraphrase one of the early director generals of CERN, there is no amount of applied research that you can do on a candle which would lead you to developing a light bulb or even an LED. So that's what CERN's doing. CERN is understanding how the universe works at a more basic level, fundamental research, finding out the basic laws of nature. And to do that, we need to look a little bit of history. So, back in the early 17th century, we had Johannes Kepler. He had basically modeled the planets and understood how they were orbiting the sun and come up with formulas which accurately described the motion of the planets. Around about the same time, Isaac Newton, who had famously discovered gravity, had also created formulas which could measure and describe the motion of objects. And it was around about this time that a student, Max Planck, was speaking to his professor and asking for advice on what he should study next. And at that time, the understanding was that physics was basically done. There was nothing left to discover, basically crossing the T's, dotting the I's, but we'd pretty much modeled the universe and we knew pretty much exactly how things worked. And so physics was really not an interesting subject for such a talented student as Max Planck. But then, a few years later, there was the famously failed experiment by Albert Mathieson and Edward Morley. What they were trying to do is, at the time, the current theories of how light propagated through the universe, there was a substance called ether, which permeated the universe, and light traveled through it. So what they advised was an experiment which they were using the fact as the Earth orbited the sun, you would come into a headwind of ether, and so you'd actually notice that the speed of light would change. So they conducted the experiment, and of course discovered that the speed of light is the same in all directions all the time. And in fact, that discovery ultimately led to Einstein's theory of special relativity. 10 years later, J.G. Thomson discovered the electron, and that ultimately led to the discovery of the atomic nucleus. And round about the same time, fortunately after ignoring the advice of professors, Max Planck studied blackbody radiation, and that ultimately led to the understanding of quantum physics. Today, current theories can only account for around about 5% of the visible universe, quite different from when Max Planck was a student. To better understand the universe, the best way to do it is to go back in time, to try to understand how it all began. With satellites and telescopes, cosmologists and astrophysicists have made great strides in this area, but there's a limit. Around 380,000 years after the Big Bang, just around about here, the universe before then was too hot, and light simply couldn't escape. Effectively, the universe was opaque. But there's another way. You can try to recreate the conditions that existed shortly after the Big Bang. And to do that, you need particle accelerators. And the LHC is the largest and most powerful particle accelerator that exists in the world. And we can get closer to the beginning of time than anyone else, to a millionth of a second. So what do I mean by particle accelerators? Well, to explain, I think it's probably the best with an illustration by playing a little game that I like to call Angry Apples. So here we have a particle accelerator. The two particles in this case are two apples. And what we're going to do is do an experiment to see what happens when we accelerate them and collide them together. Okay, let's start up the accelerator and bring it up to a level 1 collision. Everyone ready? Go! Oh, okay. I think this is probably one of the most least exciting experiments that I've ever done in my life. You basically roll into each other and stopped. I think if we want to see a little bit more interesting physics, we're going to have to reset and increase the energy up to level 2. Okay, I'm sure this will be much more interesting. Let's go. Uh-oh. Okay, so we've got a bruised apple, a little bit of a collision, but really not that much interesting going on here. So I really think if we want to do something a bit more interesting, we're going to have to reset and push the energy up even higher. Okay, this is a level 3 collision. This is going to be good. Go! Ah, okay. So we've turned apples into apple puree. Not the most interesting experiment we could do. And I think all of you will understand that all these levels of the collisions are basically things that you would experience in everyday life. Ideally, not too much level 3, but these are fairly typical things. Nothing unusual has happened. But that's not what we do at CERN. In the particle accelerators we have at CERN, we put enough energy, incredibly high levels of energy into the particles. And then something quite different happens. Let's have a look and see what happens then. So let's push the energy right up to the very maximum. Everyone ready? Go. Whoa! Okay. So we started off with 2 apples, and now we've basically ended up with the content of a fruit bowl. Oh, wow, look, we've even got a cube beret. These are it. Oh. It's already deconstructed back into 3 blueberries. Oh, well. So what's going on here? Well, in fact, all that's happening is the application of probably one of the most well-known physics formula in the world. E equals mc squared. A simple equation that says so much. E, of course, on the one side is energy. And on the other side, we have m for mass and c squared. Okay, c squared. C is the constant, the speed of light, or 300,000 kilometers a second. And when you square it, it becomes a big number. But what this equation is effectively telling us is if you can get enough energy into a small enough space, you can actually create matter. You can create something from energy. There is an equivalence between the two of them. The problem is that c is such a big number, you need an incredibly high amount of energy in order to create any amount of mass. And at CERN, we have an incredible amount of energy squeezed into a proton. That's why we don't have a large apple collider at CERN, of course. We have a large hadron collider, or in our case, protons, because you need to squeeze the energy into a tiny amount of space. And apples are just too big to be able to accelerate. So we put a huge amount of energy into a single proton. 7 tera-electron volts. I'm sure this is a scale that's very familiar to all of you. No, me neither. So I guess it's about the energy of a cruise ship going through the ocean. Actually, no, it's not as much as that. How about a racing car? No, it's not even as much as that. How about a guy on a bike? No, it's not that either. In fact, 7 TeV corresponds to about the average energy of a well-fed mosquito. The only difference is we take all of that energy and squeeze it into a single proton. Now, your typical mosquito has 100 sextillion protons in it, 10 to the power 23. And we squeeze all of that into a single proton. That's the incredible levels of energy that we're talking about. So how do we do it? Well, we use particle accelerators. And it all starts with a bottle of hydrogen. You probably already know that hydrogen is effectively a proton and an electron circling around about it. So the first thing we do, of course, is to get rid of the electron. And we do that in a device with a super sci-fi name called a dual plasmatron proton source. So we rip off the electron, And the protons travel into the first accelerator that we have. This is the linear accelerator, the LINAC. And the protons enter at one end, and through different charge plates, we actually push and pull the protons as they go through the machine. Within 45 meters, they're already traveling at 100,000 kilometers a second, 1/3 of the speed of light. It would be impractical now for them to carry on in a straight line. So the first thing we do is we gather them together into a small accelerator ring called the proton synchrotron booster, where the protons are gathered into bunches and then pushed into the first and one of our oldest accelerators, the proton synchrotron. This is a circular accelerator, 600 meters in diameter. Within 1.2 seconds, the protons are accelerated to 99% of the speed of light. But at that point, this is our first gear. We can go no faster, so we have to transfer it into our next largest accelerator, the super proton synchrotron. We're not very good with names at CERN. Within the super proton synchrotron, this is 7 kilometers in diameter now. It takes around 3 seconds to get to 99.998% of the speed of light. At that point, we can't go any faster anymore, so we go to the next larger accelerator, the Large Hadron Collider. There, the particles are sent in opposite directions around a 27-kilometer ring, and after 20 minutes of full acceleration, they reach the maximum of energy of 7 TeV, or in other words, 99.9999991% of the speed of light, at which point we bash them together. Inside the tunnel, this is what it looks like. This is a long string. The blue objects you see here are the dipole magnets, which actually keep the particles in line. These are electromagnets running at superconducting temperatures. The field strength within the magnets is around 9 Tesla, or about 200,000 times that of the Earth's magnetic field. To do that, we pass 12,000 amps through the cables. In fact, the magnetic field is so strong that it actually exerts a bending force on the magnet itself of around 400 tons per meter. That's about the weight of a Boeing 747. So they have to be made incredibly strong. In order to make sure the protons don't hit anything as they go around, the inside of the pipes are actually evacuated to very high vacuum, 10 to the minus 13 atmospheres, or about 1/10 the surface of the moon. And to keep everything running, we have to keep it at cryogenic temperatures, minus 271 degrees Celsius, actually a degree colder than you find in outer space. As many of our physicists say, CERN really is the coolest place in the world to work. And the whole thing is held in a tunnel underground, about 150 meters underground. These large installations you see here, these are the actual facilities where the detectors are housed. Cathedral-side constructions actually built underground. The whole thing, as you can see, sits under the French countryside, near the city of Geneva. In the background there, you can actually see, that's Mont Blanc, in fact. And my house is around about here, actually. That's where I live. So the whole thing basically sits in the French countryside underground, this enormous installation. Inside, the protons are going around 11,000 times a second around this 27-kilometer racetrack. They're gathered into bunches. There's about 3,000 bunches, and each of the bunches contain about 100 billion protons. They go around the ring, and at a certain point, we squeeze them together. So the bunches are actually, the diameter of the bunches goes down to about 1/3 that of a human hair before we line them up and actually hit them end to end within inside the particle detector. The detector itself is effectively a large 3D camera, and it detects all of the traces of all the particles that come out. There are around 600 million collisions a second. The raw data rate from a single detector is around 2 petabytes a second. This is way too much data to handle, of course, and in fact what the experiments are looking for is actually quite rare. As each bunch crosses, there's 600 million collisions a second. As each bunch crosses, there's only usually around about 19 actual head-on collisions. So most of the data we can throw away. We only actually keep about 1 in a million of these actual traces. The rest of them are actually discarded very early on using specialist hardware. Just for a sense of scale, this is a photograph of one of the real detectors. This is Atlas. Down at the bottom here is a person, to give you an idea of a sense of scale. This is one of the 4 large experiments in CERN. Atlas is probably one of the most well-known. The other 3 are ALICE, CMS, and LHCb. It was Atlas and CMS were the 2 detectors which announced the discovery of the Higgs boson back in 2012. Together, the four experiments produce a raw data rate of around 10.5 gigabits a second, which we've got to store and process in our data center located in the center of the CERN site. On site, we've got around 166,000 processor cores and 150 petabytes of disk. That's around 60,000 individual drives. And in the basement, we've got another 240 petabytes of tape operated by tape robots, and we expect to store around 50 petabytes of data every single year. I mean, 166,000 processor cores might well sound a lot, but it's nowhere near enough to process the data that we want. And in fact, that's why we created the LHC Computing GRID. LHC Computing GRID, this is CERN at the center here, is effectively a network of computers all joined together with high-speed links. There's a central core, which is what we call the Tier 0 site at CERN. And then outside there is a further 11 data centers spread across the planet where we send a copy of all of the data to them. Beyond there, there's the Tier 2 sites where the actual data processing takes place, and these are data centers located in physics institutes and universities across the planet. The LHC Computing GRID effectively builds a planetary-sized supercomputer in order to do all of this data processing. There's around 2 million compute jobs running at any one time on the LHC Computing GRID. To operate such a device, of course, takes a lot of technology. This is a photograph from the inside of the LHC control room. On the wall at the back here, you can see all these fixed displays used to monitor the operations of the machine. And the consoles around here are actually used by the operators to actually drive and control the machine. Interestingly, Java has actually played a key role at CERN since the very beginning. And in fact, most of the screens you see here are actually running Java applications. In fact, Java has been at CERN since its very beginning. This brings back memories, good old Windows 95. And just about then, Windows 95 and the web, this is what it looked back in 1995. And it was around about this time, in fact, that CERN started looking at Java. Java wasn't really available in many platforms, and in fact, the first real platform that did anything with Java was good old Sun's hot Java browser. As a browser, it brought some kind of interactivity that really people had never seen before. 3D graphics, well, nearly. And basically, they kind of had an opportunity there that we felt it was going to drive something really quite amazing for us. Soon, Java became more ubiquitous. It was entering applications like Netscape Navigator, good old tumbling Duke here. And that was around about this time that I started developing the first Java applications. And in fact, the first one I wrote was actually a single sign-on application. This was at the time when HTTPS was seen by our server guys as a bit of a risk because it might introduce too much load on the servers. So we had to actually build the application around using insecure connections. And so this was my first JDK 1.0 application, where I was doing encryption algorithms, lots of bit shifting and manipulations, long before the libraries ever existed to actually do this kind of encryption yourself. And what tool did I use? Well, Visual J++, of course. But it was clear that Microsoft and Sun had different ambitions for the Java language, and they soon parted company. And we switched to another IDE, the well-known Visual Cafe, starting off as beginners, then moving on as to professionals, and then ultimately as experts, well, at least as far as the product titles were described. After Visual Cafe was no longer working on our Windows NT servers, we had to switch to a new tool, and we picked JDeveloper. I'm not saying it was the best choice I've ever made, but one of the big advantages of this tool was every time it started up, it reminded me that with productivity comes choice. So we chose Eclipse. And then moved on to IDEA as well. And these days, in fact, most of the developers are using IntelliJ. And what are we doing with it? Well, from the group that I'm responsible for, we're running actually CERN's business function. So all of the administration of the organization is operating on Java. Our workflow system and business process engineering system is all built on Java. Our decision support system, data warehousing, all of this, based on Pentaho, is all based on Java as well. And in fact, all the project management tools that we developed to actually build and construct and operate all these multi-million-dollar projects were actually built using Java technology as well. But beyond that, we actually run the machines using Java as well. This is a screenshot from one of the consoles, which is actually the control panel for the accelerating cavities, superconducting radio frequency cavities, which actually accelerate the photons within the LHC. This is a beam diagnostic screen made in Java as well. This is actually showing the profile of a single bunch of protons within the LHC. There's a convention within the control room that the red beam goes clockwise and the blue beam goes anti-clockwise. Here is an end view of a beam, again written as a Java application. And this is quite nice because it also shows you this is actually a profile of all of the bunches in the LHC of all of the protons. And it's not just actually operating the machine as well. We also have the slow controls, which actually control all the various slow functionality within the accelerator complex as well. This particular synoptic chart is actually monitoring the airflow of all the ventilation system within the LHC. There's around 120,000 sensors all over the LHC complex itself, all bringing data to this particular application, around 100 million data points a day. And the operators themselves compose these synoptic charts themselves from a palette of information which is available to them on the side. And as well as that, from the same tool, they've got around 1,000 different control channels that they can use to actually operate the different pumps and switches and valves and actually to operate the LHC slow control system. Outside of CERN, the Atlas collaboration, we're using Java 3D to model and visualize the Atlas detector along with the particle tracks within inside it. And further afield again, Imperial College in London, together with the Blue Marble data from NASA, actually made a visualization tool to visualize the LHC Computing GRID and all the jobs which are actually traveling back and forward across this worldwide computing grid. In fact, it was in 2008, just before the end of the very last Java 1 operated by Sun Microsystems, that CERN was actually very honored to receive the Duke's Choice Award for the use of Java across all of the different control systems and all the different areas that we have Java at CERN. One of the things I did want to highlight, an application which I'm particularly happy about, is the public outreach application. This tool actually embeds the essence of CERN. As an open laboratory, you're welcome to come and see it. Come and have a look. This tool actually helps us organize all the 120,000 visitors that we have coming to the organization every single year. There's around 4,200 visits that were organized just last year alone, and you are welcome to come. There are 2 permanent exhibitions open all the time, and at the same time, if you sign up via the website, you can actually sign up for a guided tour as well. And more importantly, they're all free. I've only just scratched the surface of CERN here. But of course, there's things like the antimatter factory, which I'd like to talk about for a second or two. This is quite near the second restaurant, and is the largest concentration of antimatter in the known universe. We're actually creating antimatter on a regular basis in order to study it in more detail, trying to understand why, in fact, there's the early universe, why matter took the preference over antimatter. We've got the Isolde experiment, which is creating radioactive isotopes for nuclear medicine. The cloud experiment, which is actually using detector technology to understand how cosmic rays are affecting the planet's climate and the cloud formation. And of course, we have the AMS detector, which is actually a particle detector built and constructed at CERN, which is now part of the International Space Station and operated from a control room in CERN itself. As an organization, CERN is a unique place, with world-leading physicists like Richard Feynman, Stephen Hawking giving lectures at CERN. The World Wide Web was first announced there. And as I mentioned earlier, in 2012, the Higgs boson, the particle responsible for giving bodies mass, was actually identified and discovered and ultimately announced at CERN. Personally, I think the Higgs boson was very important to me because for a long time I was pretty sure that my mass was mainly responsible for drinking too much beer and eating too much pizza. But as I now understand that, in fact, all it is, I interact more strongly with the Higgs field. I did give this explanation to my wife, but she wasn't quite so convinced. CERN is really a place of extremes. Enormous engineering feats, cathedral-sized detector structures built underground to study the most minute phenomena, subatomic particles. And at the heart of it is computing. Computing is everywhere at CERN, from the data centers, from the control systems, from the accelerator complex themselves. There are teams of IT professionals working at CERN. CERN, at its core, is infrastructure, providing all the facilities to do physics. There are IT engineers creating data, pushing data around the planet, monitoring the systems, developing new software. In fact, even most of the physicists I know write software, although admittedly I wish sometimes they wouldn't. It's an open lab. Please come and see us. You might recognize some of the people in some of these photographs. But these are examples of the open day that we had at CERN, where we had people coming to see and actually go down and look at the accelerator complex. You're welcome to come at any time. You should come at any time. It's free to visit. And actually, very interestingly, in 2019, the Large Hadron Collider will be actually shut down for a major upgrade. And during that time, you'll have the opportunity to actually physically go down and see the detector complex yourself, go into the tunnel, and actually look at the detector and see how it all operates. And so to coincide with that major shutdown, we're actually running again 2 major events in 2019. First of all, we would be very happy to run another Voxhead Days at CERN. It was very successful last time, and I think it would be really nice to do it all over again. And that will be in the spring of 2019. And then later on in the autumn, there will be a full open day. The last time we did an open day at CERN, we had nearly 100,000 visitors in a single weekend. We're expecting to have even more this time. So you're very welcome to join us again in 2019, unless you want to, of course, come before and visit on any of the organized visits that are there. In this presentation, I have just scratched the surface. In fact, it may be a little odd for a British person in the age of Brexit to be talking so highly of a European institution. But I think this is somewhere that all of us can be proud of. There have been discoveries made at CERN which has literally changed the lives of probably everyone in this room. And we continue to make more and more discoveries. It truly is a remarkable place that I think is a highlight in European technology and European science. And I think it's something where everyone should be justly proud of. So on that note, I would like to thank you.